Howdy peeps, Doc here. According with the Blackboard announcement that I made earlier, looking to make a video here to show you how to analyze the data from the chemical engineering team project that we just completed. So to do that, I'm going to switch over here to the template. So the blank template is pretty much like this. I'm going to slip in the data from my experimental run. So this is what I got when I ran through everything. Your data, of course, will look different, but that's okay. I'm going to show you how to run through this. So every cell that's been boxed in requires us to put something in there. And so here's the raw data we've collected from the experiments. And now all that remains is for us to put in the calculated values. So to start off with reaction rate, which of course is the mass of the product that comes out divided by the time for the reaction. So I'm just going to take this cell and subtract out this cell. Actually, no, divide. I get my operators right here. There we go. That looks better. And then we can just go ahead and copy this down. But first I want to get this formula here so we can just copy everything down at once. The profit is going to be the revenue minus the cost. So if I come down here to my cost calculations, I really need to fill this area in first before I can calculate the profit. So we'll start here with the surface prep costs. The costs are located on the following tab. Notice how there's something of a table here. And the value that we're going to have to put in any individual cell is determined by the surface prep factor. So how can we actually automate this so that we don't have to keep manually putting in each one at a time? And there's a great function in Excel for doing that. It's called VLOOKUP. So if I put in equals VLOOKUP, and then notice the syntax here for the different variables it's looking for. The first is, what value are we going to be looking up? And that's going to be the surface prep factor. So for that first run of our experiment, the surface prep factor is this cell right here. I want that cell to change as we move down with the different experimental runs. So I'm just going to leave that as is. So put in a comma. And now the next thing I'm looking for is the table array. So this is basically, where's the table that we're going to be looking up values in? And that's on the following tab. So I go to the following tab, and I'm going to select these values here because this is the table, so to speak, where we're going to be looking up values. And because I want this to stay the same, this reference for these cells to stay the same, no matter which experimental run I'm doing it, I come and press F4 on my keyboard, and notice here in the function how the formula put in the dollar signs. That's assigned to Excel that says keep this reference constant. So when you copy this down or over to adjacent cells, those references to those cells are not going to change. So there's our table. Now next we need the column index number. So what this is the number of the column that you want returned. So it's going to be looking up values here in the first column. That's just by default from the way that the function's set up. What we want returned is the number in the second column. So I'm going to slip in a 2 here. And then this range lookup is actually it's an optional function. We're not going to need it for our purposes, so I'm going to close out my parentheses there, hit enter, and it gave me a value of 0. Now that is the surface prep cost when I have a surface area factor of 1. Look what happens when I copy this down. See all those where I had a different surface prep, it actually gave me something different. So, and it actually gives me the right values. So that portion is actually automated. I don't have to go back and forth And that's a very useful feature of Excel, VLOOKUP. There's a corresponding HLOOKUP, which is looking up along rows instead of columns. And in my practice, I haven't really used it that much. VLOOKUP has been the one that's been pretty much a standby. It's a very useful function. So let's look at next calculating the solute cost. What's the cost of the solute? Well, the cost of the solute is going to be equal to the amount that we used. So for that first run, it's going to be this cell. And that's going to be multiplied by the cost per unit of solute, which is this cell right here. Again, I want this reference to stay the same. So I put in those dollar signs by hitting F4. And that's all I need for that function. Solvent costs are going to work the same way. Come back up here. Here's my solvent. Multiply that by unit cost. Again, keep that constant. Operational costs. That's related to the reaction time. So I'm going to come over here, click on my reaction time. Multiply that by that unit cost. Keep that constant. And then this is just going to be, whoops, I learn how to type. Sum of those three cells there. And then, of course, revenue, we're assuming that we're selling all the sludge that we produce. So I come over here and say I'm going to look at the sludge that came out and multiply that by its unit cost. Keep that constant. Boom. So now I've got those formulas. Now all that remains is to copy them down. Notice how this last row for proof of concept didn't really produce anything, and that's because we don't have any data here yet. That's going to come last. We'll get to that when we get done filling in all of our charts. And we're almost to that point, because now that we've got our cost calculations figured out, now all we need to do is come up here and figure out our profit. Profit is going to be equal to the revenue minus the total of the costs. And there's my profit. So if I copy you down, and now you can see I've automatically populated my charts. And we can see where the profit is actually the highest. You can also see it by looking at the tabulated values. It's going to be somewhere here in this range. So for the values that I'm looking at somewhere in the $2,000 to $3,000 range for maximizing my profit for each experimental run. And that's pretty much clearly shown here. If you look at this, this is the place where the profit's maximized here on the graph. So I can verify that by looking at linear regression. Or I don't even know that it's linear. We can also look at nonlinear regression. If I come down here and look at my other variables, I can do the same thing with these values here. See where everything's kind of maxed out. First, let's go look at the reaction rate versus profit. Where's the profit maximized? Well, you can look clearly here on the scatter plot and see that it's going to be here in this range. But let's just do a regression analysis. And to do that, I'm going to click on one of the data points, doesn't matter which one, and then while my cursor's still there by that data point, I'm going to right-click on the mouse, and then down here in this menu, I'm going to select Add Trend Line. Now, it assumes that you want a linear fit, but there's other nonlinear fits that we could look at, and we should probably look at those. So let's check out here to know which of those is actually going to fit our data best. I need to click this box here for display R-squared value on chart. Sometimes it's also helpful, especially if you're going to be using the actual model that's created from the data. Click on this display equation from chart, and that gives me the mathematical model that represents my line of best fit for my data. But the value I'm really looking at is just R-squared value. So R-squared can vary between 0 and 1. And what we're doing is trying to get R-squared to be as close to 1 as we can get it to be. So notice here how it won't let me do an exponential fit to the data, but I can do a linear fit or I can do a logarithmic fit. Notice how R-squared value went down. That means it's a worse model. Polynomial fit, 0.89. What do we have for linear? 0.84. So the polynomial model, second order polynomial, actually makes a better fit for my data. So looking here at the data, I can change the order of the polynomial if I want. I can go third order, fourth order, fifth order, but that just makes the model more complicated. Even though I get a better R-squared value out of it, I get a more complicated model out of it. And simple is usually better. So let's just keep this back at the second order. So I can look at a second order polynomial, the 0.8924, and again, you can see that the line of best fit predicts that the profit is going to be looking at where we've got a reaction rate somewhere around, it's probably what, 0.25 if I click on this, and let's format the axis. Change that a little different. Look at the number. Yeah, it's put in 2 decimal places. So it looks like our reaction rates are maximized between 0.15 and 0.2. So that's going to be useful information for us when we go to look at these charts down here. Notice here we're comparing reaction rate with each of the different variables that we were changing in our experiments. So we can do the same sort of analysis with each one of these charts. If I click on here at the data point and then right click my mouse, I can add a trend line here. I'm going to scroll down here to get that R-squared value. So linear fit 0.9718 is probably the best we're going to see. Yeah, that's a little worse. That's a lot worse. 0.9768. 97. And then moving average is something you typically don't use that when you're doing regression analysis. So just focus on the first 5 here. So it looks like it's 0.9768, 0.9718. So slightly better with the second order polynomial. I'm just going to go ahead and use the linear. Linear is simpler than polynomial, and the difference 0.9768, 0.9718, not all that different. So I'm just going to go with the simpler model and just click on here. So we can see we maximize the surface area, you're going to maximize your reaction rate. I can go and do the same thing here with the next chart. And let's see what we got here. So scroll down and get my R-squared value. So linear fit gives me 0.81. Exponential, that's worse. That's much better. That's even better, 0.99. Yeah, we're not going to do better than 0.99. So I'm just going to keep this. I click on that, I can actually move that so it's out of the way. See, this is why we do 5 data points, because if I only did 3, then I'm more likely going to get just a linear fit. But you can see that the second order polynomial is a much, much better fit for the data than the linear model. So that's why we do 5 data points. So if there's some sort of curve in the data, it's more likely to be revealed with 5 than 3 data points. And we can see that the reaction rate here is going to be maximized when we have a mass of the pellets between 1.5 and 2 grams. If I go back and look at my data, the mass of the pellets between 1.5 and 2 grams, it's going to be this value right here. So let's go ahead and finish out with the third chart here. And then we can go ahead and figure out what our proof of concept run should be. Trend line. So here we're going to get the R-squared value. Move that out of the way. Okay, so 0.649 with the, go back to my trend line, 0.6491 with the linear. That's not much better. That's a little bit better. That's quite a bit better. 0.68. I think the second order polynomial is where it's going to be 0.79. Yep. So that second order polynomial is where we want it. Of course, the maximum is going to be here where we're actually using less water. So if I look at the variables that are going to maximize the reaction rate to give me my maximum profit, okay, because that's what we learned up here. Profit is maximized when we maximize reaction rate. So if I come down here to my different variables, what values of these variables maximize reaction rate? Well, here for surface factor area, I want the highest surface factor I can get, which is going to be the 16. So here for proof of concept, I want 16 to be my surface factor. And looking at the next variable, mass of the pellets, that reaction rate is going to be maximized if I have, as I saw before, between 1.5 and 2 grams for my pellets, which if I look at my data here, that's the value there that's between 1.5 and 2. That corresponds with 8 pellets. So I want 8 pellets here. And then the mass for the solvent, the water, it's going to be as little as I can get away with, which for our experiments was in the neighborhood of 50. So I can just put that in there. And then that's pretty much all I've got here from my different variables. So with these data then, I could actually run another proof of concept experiment. Now, if you didn't get to this point in class, then the only thing you have left to do is to make some what we call engineering estimates, otherwise known as an educated guess. So if I've got 8 pellets, I can use the same mass that I was using before for the 8 pellets. Just use the same mass here. So that's going to be 1.7. And then the mass of the sludge out. Well, let's just assume that we're going to get, the same amount in. I know we've got a lot more water here for this run, but if you look at your chart here for the reaction rate, there's a little bit of a curve here, but it's not going to make that much of a difference here. So if we wanted to, we could actually just say we're just going to get the same mass out that we did with the 8 pellets. So that's going to be, yep, the 10.4. And let's just, how do we estimate our reaction time? Well, I would think reaction time would probably go up a little bit. Surface factor 16. So the reaction time here was 17, but we've got different mass here. So why don't we I'm going to select both of those cells and take the average of both of those. If I look down here at the bottom of my Excel screen, when I select both of those cells, the average is 39.4. So let's just go ahead and assume that's what we're going to get here, 39.4 for that. So then our reaction rate is going to be, we got out, divided by the time. And of course, profit is going to come from the difference between these values down here. I'm going to go ahead and just put that formula in. We're going to have to correct these values here, which we're going to do directly. So of course, it doesn't list anything here because we've got to update this. Those cell references have to be adjusted because what we want to look up is not NC18, which is this cell here. What we want to look up is this cell here. So I got to change the 18 to a 21. And that updated that value. So now if I come over here to solue costs, notice I've got to update that 18 to a 21. And this gets updated to a 21. And this gets updated to a 21. And now my values here are all good except for this one. I'm going to update that one to a 21. Now my values are all good. And we can look up here and look at the proof of concept. I'm way better than any of my experimental runs. So this is definitely proof that these are the optimal values for my reaction. And that's basically how you run through it. So I hope this helps some of you. And if you're familiar with Excel, I hope you're able to learn a couple things that might help you to use Excel a little bit better. If you have any questions, of course, shoot me an email. I'll do what I can to help. And other than that, I'll see you guys in class next time.